Hello, Gearing Up. My name is Mark Hung, and I'm a third-year integrated sciences student. And this is my teaching video. Today I'm going to be talking about membrane transport, which I feel is a vital concept that any student looking into learning more about biological systems and fields such as physiology should definitely become very comfortable with. So there are actually two divisions of transport mechanisms. We're going to be talking about passive transport first of all, and this is characterized by distinctly not requiring energy. Why is this? Is because it uses gradients such as electrochemical or chemical gradients to drive ions or molecules across the membrane. So the first type of passive transport we're going to be talking about is simple diffusion. It really is simple because molecules just straight diffuse across the membrane without any aid necessary, for example from transport proteins or transport carriers. Now only a certain amount of molecules are actually able to do this, or certain types of molecules are able to do this. Distinctly gases, for example oxygen or nitrogen, some other examples mentioned here, but other molecules that are able to do this are going to be having to be hydrophobic, and this has to do with chemical structure. So normally these hydrophobic molecules are going to have to be nonpolar and non-charged. An example you might be familiar with are steroids, or steroid hormones, thyroid hormones, all that jazz. As you can see, as mentioned, we're using the gradient to move ions across the membrane. So, for example, moving from high to low is always the case for passive transport. The second type of passive transport we're going to be talking about is facilitated diffusion. Rather than just diffusing right across the membrane without any aid necessary, we're actually going to need proteins, the use of proteins. In this case, we're going to be talking about two specific proteins, the ion channel and the permease. Okay, so the ion channel, it's really just a channel or a pore, you could say. And again, we're using high concentration to low concentration, as illustrated here, and as with the particle amounts, as demonstrated in the diagram here. Yeah, so these molecules will just move across. But there's actually a great deal of specificity. For example, let's say this ion channel is a sodium channel, or sodium ion channel. It's really only going to let sodium across, but specificity is such a complex topic that we're definitely not going to touch on that today. Permeases. Permeases are more interesting in that their mechanism of movement of ions is more special. It's not just a pore. First of all, molecules will bind to the binding site, which is exposed to whichever side of the membrane you are moving from. Okay, binding of the substrate to this protein structure, the permease, at the binding site, is going to trigger this conformational change of the permease. Now, what is a conformational change? It's basically a change in the protein structure that alters shape and oftentimes function. Okay, and basically you create this shape change or movement, or shape change or structural change that allows this ion to be transferred, ion or molecule, to be transferred over to the other side. Okay, and some examples of ion channels are aquaporins, they transport H2O, water, specifically. Sodium channels, potassium channels, these are in great amounts in your typical cell kind of demonstration. And permease, an example of permease is the lactose permease, for your information. So now we're going to be talking about active transport, which is the second dimension to transport, and this uses or involves the use of ATP, either directly or indirectly. And we'll talk about how ATP functions in allowing for active transport to be carried out. So there are two types of active transport. We're going to be talking about primary active transport first of all. Primary active transport is the simpler of the two, and basically involves you have some kind of protein or membrane transporter that allows for, in this case, solute or substance X to move across the membrane. But notice, as opposed to our passive transport cases, that in this case, X is trying to move from low to high concentration, or rather, the side of the membrane with low concentration of solute X to the side of the membrane with high concentration of solute X. Now this is against the concentration gradient, which is always going to require energy. So that's why we're going to need energy. Where do we get energy from? We get it from ATP. Okay, ATP is a very high energy molecule because it has a high energy bond, specifically between two molecules, which ATP breaks down into, ADP and the inorganic phosphate. So when this high energy bond is broken, then energy is released to be used into transporting the molecule from an area of low concentration to high concentration against its concentration gradient. And here are some examples. The proton pump, sodium or potassium, or any other naturally occurring kind of metal ions in the biological systems. They require pumps. And the sodium-potassium pump, which is a very important pump that you'll learn about, especially when you start delving into the field of physiology. Lastly, we're going to be discussing secondary active transport. Basically, there's going to be two steps involved in secondary active transport. Secondary active transport is going to involve the first step being essentially what happens with primary active transport, where you use ATP hydrolysis, which is breaking down ATP. I should have mentioned that earlier, but you use ATP hydrolysis to create this chemical gradient or electrochemical gradient. So let me illustrate that here. So as you can see, X, we're trying to move it from an area of low concentration to an area of high concentration. As you can see, lots of substance X being accumulated on this side. Now how do you do that again? You're going to need energy. So where's that energy come from? It comes from ATP hydrolysis. So as you can see, we break down ATP by cleaving that high energy bond, or breaking that high energy bond, and that energy goes towards moving X against its concentration gradient. Okay? Now interestingly enough, when we do this, we actually produce chemical or potential energy that we can actually use later. We can harness and take. So this is the generating energy step, essentially. Now how do we harness this energy? Well, we can harness this energy when we have to move another ion or another molecule across the membrane. But we have to move, but usually, of course, we need energy to move an ion or molecule against its concentration gradient, right? So in this case, that other ion or other molecule that we're trying to move across the membrane, we're going to be trying to move it against its concentration gradient. As you can see, that would be molecule Y right now. Again, molecule X, we already put in the energy, right? So we established this concentration gradient. So we're not going to need any more energy to get X back to the other side, because it's just going to diffuse down its concentration gradient. But Y in this case is just going to tag along, and because we put in energy to through ATP to develop this chemical potential energy, we can harness that energy just to move Y against its concentration gradient without adding any further energy. Okay, so that's basically the that's the mechanism. Oh, sorry. That's the mechanism of secondary active transport. And there's two cases having to do with or differentiated by the direction of molecules, their movement specifically. So antiport and symport are the two that we're going to be looking at. Antiport, and then I should note that they're specifically referencing this second part of the secondary active transport after you've produced that potential energy in the form of chemical gradient. Okay, so antiport means essentially opposite. So in this case, X and Z, Z is the molecule that we're trying to harness that energy that we used from creating this chemical gradient of X to transport Z across. So Z is going to be moving in an opposite direction to X, and that's what we're going to call antiport. Okay. Conversely, if we're trying to move, the molecule that we're trying to move across, in this case, Y, is going to be moving in the same direction as X, we're going to call that symport. Okay. So basically, antiport, opposite directions of movement, and symport is going to be the same. Yeah. So antiport. So I guess membrane transporters that operate using the mechanisms of antiport, we're typically going to refer to them as exchangers. And for symport, symport operating membrane transporters, we're going to be referring to them in a general sense as co-transporters. Thank you.